Okay, welcome everyone to, I believe it's the 6th guest lecture at this point. And I'll leave it up to David now.
Yeah, hey everybody. My name is Dave, or Mr. Knott, depending upon how formal you want to be. And I'm going to talk about abstract algebra, in particular group theory, and do some applications to number theory. I think the reason that I chose to put a little bit of an emphasis on number theory is basically because I know that a lot of students in the high school level and beyond that as well are interested in number theory. I think there's a lot of number theory in the mathematical sort of competitions that people get involved in, and it's just kind of a common subject that people go after. And so for that reason, I've decided to kind of flavor my group theory with a little bit of number theory. But I want to emphasize that group theory is a very broad subject within mathematics, and number theory is the location of some of its applications, but group theory is something that people study in its own sake. It's not just like in support of number theory or something. And so I just wanted to point that out and emphasize that the material that I'm going to go through has much broader applications that I'm letting on. It doesn't just apply to number theory, but a whole host of different things. Okay, so I'm going to try and get through as much as I can without going too fast. You know, as with everything in math, I'm going to start with a definition. And the very first thing I'm going to define is a group. So a group is a set. Okay, it's a set, kind of like most things in math are really just sets of one kind or another. A group is a set. I'm going to call it capital G. But it's not just a set. It has an additional thing that goes along with it called a binary operation, a binary operation. So it's a set G along with a binary operation. And I'll explain what that means in a second. And I'm going to give this binary operation a name. I'm just going to call it dot. Binary operation just means it takes two things and smashes them together into one thing. Just like multiplication, right? Multiplication, you have two things and you multiply them and then you get one thing, right? So this binary operation, I'm representing it with a dot. So it could literally be multiplication, but it could also be any other kind of binary operation. So it could be plus, like addition of numbers, or it could be like matrix multiplication, or it could be like function composition, or all kinds of different things. So just understand that even though I'm using the multiplication symbol, it doesn't literally necessarily mean multiplication. So yeah, so a group is a set G with this binary operation, but the big idea here is that this binary operation has to satisfy some properties, okay? And here are the properties. So it's a set G along with a binary operation dot, such that, and there are going to be three properties that need to be satisfied for this thing to be a group. So first of all, there has to exist. So I hope you're familiar with this symbol. It's a backwards capital E. It just means there exists. Okay, so there exists a special element, okay, which I'm going to call E. It's not like E from, you know, pre-calculus. It's not 2.71. It's just the letter E. So there exists this special element called E, which is an element of G. I hope it's clear again. This funny little like euro symbol here means element of. I don't know how familiar you guys are with that symbol. So there exists this special element in G such that, and here's the problem. Basically, G dot E has to be the same thing as E dot G has to be the same thing as G for all G in G. Okay, and again, this upside down A is another one of these symbols used in logic a lot. This thing just means for all. If you haven't seen these symbols, don't be too intimidated. It's just a shorthand. So literally in English, this sentence says, there exists a special element, which we call E, in the group G such that G dot E is the same thing as E dot G is the same thing as G for every G in G. What this is saying is that there exists an identity element, okay? Identity element. That's what this E thing is. It's an element which doesn't do anything under the group operation. G dot E is the same thing as just plain old G. So if your group operation were multiplication of ordinary numbers, then your identity element E would just be 1. If your group operation were addition, then your identity element would be 0. I can't hear you, but I'm hoping that you sort of said that in your head, right? It's an element which doesn't do anything, okay? All right, so that's the first property that this group thing has to satisfy. What's the next property? The second property is basically the existence of inverses. Every element has to have an inverse. So for every G in G, so for every element in this group, there exists another element denoted G with a little -1 exponent, such that G dot G inverse is equal to G inverse dot G is equal to, now, if we want these two things to be inverses, think about what that usually means, right? Like the multiplicative inverse of 5 is 1/5. What happens when you multiply 5 and 1/5? You get 1. That's the multiplicative identity, right? So for these two things to be inverses, what we want is we want their quote unquote product under the group operation to be this identity element, whatever it is, E. Okay, so what this second statement is saying is that every element has an inverse, all right? And when you smash an element together with its inverse, you get the identity element. And then the third and final property is just that this operation has to be associative. So that just means that G1 dot G2 dot G3 is equal to G1 dot G2 dot G3. Okay, so grouping doesn't affect the operation. Notice that I did not say that the operation is commutative, right? In general, it is not true that G1, G2 is the same thing as G2, G1. In some groups, that's true, and we call such groups abelian or commutative, but in general, groups don't have this property. The order matters, but they are associative, okay? All right, so any set with any such operation satisfying these three properties is a group. So let's see some examples. So now I'm just going to give you a barrage of examples. So let's start with a really familiar example. Let's start with Z. This symbol here, like the funny Z, it means the integers. Okay, so the integers are a group, but the thing is, you have to remember, a group is not just a set. It's a set along with some operation. So for me to just say, oh, the integers, that's not enough to specify a group. I also have to tell you what the group operation is. Am I talking about addition? Am I talking about multiplication? And in this case, I am in fact talking about addition. So if you really want to emphasize that it's addition, you can sort of pair it with plus. So the integers under addition do form a group, right? Because first of all, is there, I mean, let's look at the properties and make sure that it satisfies them. Is there an identity element which doesn't do anything? Yeah, it's 0, right? 0 doesn't do anything under this operation. Does everything have an inverse under this operation? Yeah, it's the negative, right? I mean, if you give me 5, right, then the inverse of that element in this group is -5, because when you combine them, you get the identity, which is 0 in this case. And certainly addition is associative. But now let me ask you, are the integers a group under multiplication? Is that a group? I'm hoping that you're recognizing that the answer is no. And the reason why is that not everything has an inverse. Actually, most things don't have inverses, right? Like if you give me the element 5 here, the inverse under this operation is 1/5, but the problem is 1/5 is not an element of the integers, right? So 5 doesn't have an inverse in this thing, whatever it is. Therefore, this guy is not a group. The integers are not a group under multiplication. Okay, there is, well, maybe I'll skip that one. Okay, let's talk about some more interesting ones. And you can do like, you know, well, there is kind of a cute little thing you can do. You could take R, for example, and get rid of the 0 element. This thing is a group under multiplication, right? So if you take the real numbers and you just get rid of 0 and you consider that set under multiplication, that actually is a group, right? Everything does have an inverse. Like the inverse of 5 in here is 1/5, and that is an element of R. So this guy actually is a group. Sometimes this thing is called R with a little asterisk, like R star. It's the non-zero real numbers under multiplication. Okay, look, those are pretty boring groups. They're pretty conventional. Let's talk about some more spicy groups. Let's talk about something a little bit more interesting. How about the nth roots of unity? Like the nth complex roots of unity? Those actually form a group under multiplication, okay? So let's be specific and take a specific value of n. Let's say we're talking about, say, the 5th roots of unity. I don't know why I keep using the number 5. I guess it's just my favorite number. So the 5th roots of unity, if you remember, you know, they sort of, if you plot them in the complex plane, what do they look like? Well, there's always this guy right here. That's 1, right? 1 is, of course, a 5th root of itself. And then the remaining 5th roots of unity, there are 5 of them total, form like this equilateral, you know, 5-sided figure, better known as a pentagon, right? You don't have to draw these lines, but you can. So these 5 points right here, they're complex numbers, and those 5 elements form a group. And one way to check that is to you know, just sort of look at the definitions. You know, is there an identity element? Yeah, I mean, 1 is certainly an identity element under multiplication. But sort of the more interesting question is, if you take this guy right here and you multiply it with, say, this guy right here, do you get another element of this set? You do, because if you remember how complex multiplication works, what do? You multiply the modulus, like you multiply the radius, and you add the angles. So you got one angle right here, and then you've got another angle right here. If you add those 2 angles together, you're going to get the angle which points to that 3rd guy, okay? And the modulus, because the modulus is 1, remember these are 5th roots of unity, 5th roots of 1. Because the modulus of each of these 2 guys is 1, you multiply 1 times 1, you get this guy right here. So this does indeed form a group. It's quite an interesting group as well. Okay, and now, you know, I sort of said that we would be talking about number theory. This is sort of a number theory type thing, but let's talk about something very familiar from number theory. Let's talk about Z mod n, okay? That's, of course, the integers mod n under plus. That forms a group, right? So, you know, I think you guys probably know what this is, but just very quickly, like what's Z mod 5? Well, it's the elements 0, 1, 2, 3, and 4 under mod 5 arithmetic. You can check that under addition, this thing satisfies the group axioms, okay? Now, finally, one more example, which is going to be sort of a source of many of the investigations that we'll look at today, is a related object, which is U sub n. And what this is the integers, well, I sort of have to qualify this in a second. The integers mod n under multiplication. Now, I have to qualify this because if you just write down all the integers from 0 to n and look at multiplication modulo n, that actually won't form a group. In general, things don't have inverses, okay? So for example, if you just considered like, you know, under mod 4, the elements 0, 1, 2, and 3, what you'll find is that 2 doesn't have an inverse under multiplication, right? Because 2 times 0 is 0, that's not the multiplicative identity. The multiplicative identity here would be 1. So this is your E, right? 2 times 0 is 0. That's not the identity. 2 times 1 is 2. That's not the identity. 2 times itself is 4, which is really 0 mod 4. That's not the identity. And 2 times 3 is 6, which mod 4 is 2. That's not the identity either. So there is no inverse of 2, right? 2 times whatever will never give you 1. So 2 doesn't have a multiplicative inverse. Therefore, if you just consider the integers mod n under multiplication, that doesn't give you a group in general because not every element is guaranteed to have an inverse. So what we have to do is we have to sort of qualify this and say not just all integers like less than n, but actually all integers relatively prime to n. And I'm guessing that a lot of you are probably familiar with this. So really what I want to say is integers relatively prime, or coprime, as it's sometimes called, with n. That means no common factors. Okay, so just to give you a clear picture of what that means, you know, something like U10, okay? That would be the integers which are, you know, less than 10, and we don't include 0, by the way. We don't include 0, which are relatively prime to 10. So that would be 1, not 2, because 2 shares a factor with 10. 3 is in there, 4 is not in there because it shares a factor of 2 with 10. 5 is not in there, 6 is not in there, 7 is in there, right? No common factors with 10, 8 is not, 9 is, right? And then that's it. So these 4 guys here do form a group under multiplication. If you check, the product of any 2 of these guys under mod 10 is another one of these guys, and every one of these guys has an inverse, right? So like, for example, what's the inverse of 3? Well, 3 times 7 is 21, which, you know, mod 10 is 1. So the inverse of 3 is 7 in this case. So that's a really important group. It's what I'll call the unit group. And I'll come back to it a lot. This unit group is really quite interesting. And it's going to be a source of investigation for us. Okay, so what I want to do is just briefly touch on some notation. Just very quickly, typically to represent repeated applications of the same element over and over again to itself in a group, we use powers. So if I have an element G inside of a group and I write G to the third, technically what that means is G times G times G, right? Where this dot is whatever the group operation is. That's not surprising. But you might wonder what G to the 0 is. That is actually defined to be the identity element, okay? So if you have an element in a group and you raise it to the 0 with power, by definition, you know, we define that to be E, the identity element. And then as far as negative powers are concerned, like what is G to the negative 3? It doesn't make any sense to write like 1 over G to the third because G is not necessarily any kind of number. It's just like an abstract group element. So you don't want to say that. What you can say though is it's the inverse of G, right? Which we know to exist. It's one of the group axioms that every element has an inverse. So what G to the negative 3 really means is you take the inverse of G and you raise that to the third power. So what it really means is the inverse of G times the inverse of G times the inverse of G 3 times. So just to be clear on what the sort of exponent notation means in the context of a group, I just wanted to point that out. Okay, so let's go ahead and begin talking about subgroups. Okay, so I have another definition. So let's let G be a group of any kind, any old group. And let's let capital H be a subset of G. That's what this guy right here means. In case you're not familiar, it means a subset. So H is just some sub-collection of G, right? We call H a subgroup if, and there have to be some properties, there's going to be some properties that I'm going to list here. So, so what does it mean to be a subgroup? So writing it in the fancy sort of logical notation, it says the following. For all H1 and H2 in H, the product H1 times H2 is also in H. So all that's saying is that H is closed under the group operation. You take any two elements in H, smash them together, and the resulting thing will still be within H. Okay, that's all that says. The second condition to be a subgroup is that for every H in H, so pick any element you want in this subset H, the inverse is also in H. So what that's telling you is that subgroups are closed under inverses, right? Take an element in the subgroup, look at its inverse, the inverse is also in the subgroup, okay? And then finally, last property, E, the identity element of the original group, capital G, has to be inside of H as well, okay? You don't actually need all three of these properties. You can sort of derive one from the other, but I'll let you think about it. So these three properties are really what define a subgroup. It's just a subset that's closed under the group operation, under inverse taking, and also the identity element has to be in there. So that's what a subgroup is. And there's going to be a really important kind of subgroup that I'm going to mention. So, so here's a very important kind of subgroup. So let G be any group. And let's let little g just be any element of capital G. Okay. I'm going to define the following thing. I'm going to define, this is like a left bracket. I guess it's kind of like a less than sign. And then G, and then right bracket. So what is this thing? This object is a set. It's the set of all powers of G. Okay, so it's G to the first, it's G to the second, it's G to the third, it's also G to the 0, it's also G to the -1, G to the -2, all integer powers of G. That's what this thing is. So if you want to write it in fancy set notation, that's the collection of G to the n such that n is an element of Z, the integer. So it's all integer powers of G. It is pretty easy to check that this thing is a subgroup. Okay, so if you like, we can call this a proposition. This is called the subgroup generated by G. This thing is a subgroup of G. It's pretty easy to check this, and maybe I'll skip the proof because I think that you can probably just check on your own. In order to verify that this thing is a subgroup, what do you have to do? Well, you've just got to go and make sure that this set here that I've written down satisfies the three subgroup properties. Is this thing closed under the group operation? Yeah. Is it closed under inverses? Yeah. And is the identity element in there? Yeah, because, right, G to the 0 would be the identity element, so that's in there. So I'll skip the proof there. You can write it down yourself if you like. So this mechanism here, this thing, this is the subgroup generated by little g. This gives you a really great way of generating subgroups, right? Once you've got a group, you can generate many subgroups very quickly by just looking at this guy here. And that's exactly what we're going to do in one of the unit groups. And we're going to find something very interesting. So let's consider the following example. So let's consider, let's say U sub 7. So remember what the capital U means. That's like the numbers which are relatively prime to 7, right? So that would be 1, 2, well, really all of them because 7's prime. So all the numbers, you know, from 1 to 7, not including 7. That's what this thing's going to be, okay? And remember that the group operation here is what? It's multiplication, right? That's the group operation for this guy here. So I want you to think about this group. And what I want to do is consider some subgroups generated by some different elements, all right? So let's have a look at the subgroup generated by, say, 2, all right? So what is this? This is the collection of all powers of 2, positive and negative. So that's going to be, well, obviously, it's just going to be 2 to the 1, which is just itself, right? 2. It's going to be 2 squared, right? Which is going to be, well, let me actually write these down, right? So this is 2 to the 1, this is 2 squared, it's 2 to the 3rd, etc. Just to be clear where I'm getting these numbers. So that's going to be 2, it's going to be 4. And then we get to 8, right? But of course, we're doing arithmetic modulo 7, so 8 mod 7 is really just 1, right? And then if we go further and we look at 2 to the 4th power, you would actually get back to 2, wouldn't you? Right? I mean, 2 to the 3rd is 8, which is 1, but then 2 to the 4th just brings you back to 2. And you can see that you're just going to cycle through these 3 numbers again and again. So this thing here, 2, 4, 1, is a subgroup of this unit group. If you multiply any 2 of these guys, you'll remain within the group, and each one of these guys has an inverse, and so on, okay? All right, well, that's pretty interesting, at least to me, and hopefully to you, since you're here. Let's take a look at the subgroup generated by a different element. Let's consider the subgroup generated by 3, okay? So what is this? So we're going to have 3 to the 1, which is, of course, just 3. 3 squared, which is 9, which mod 7 is 2. And then multiply by 3 again. 2 times 3 is 6. Multiply by 3 again. 3 times 6 is 18. Mod 7 is 4, right? Multiply by 3 again, we've got 12, which mod 7 is 5. Multiply by 3 again, you get 15, which mod 7 is 1. And then multiply by 3 again, and you get back to 3, right? And then the process will start over again. You might be wondering, what about the negative powers of 3? The negative powers of 3 will give you the same set. Okay, you'll get the same thing. Like 3 to the negative 1 just means the inverse of 3, which I promise is somewhere in here. So this is, in fact, the entire subgroup. But what do you notice about this subgroup compared to just the original group? I'm sure you're shouting and screaming in your bedrooms or whatever. It's the same, right? It's the same thing. This is actually the entire group. And that's okay. Like, you know, it's actually perfectly valid for a subgroup to be the entire original group itself. That's actually okay. But what I want to draw your attention to is that something very interesting happened with these 2 elements, okay? This element here, 2, we looked at the subgroup generated by 2, and we did not get the entire group, right? We just got like half of it, okay? 2, 4, and 1. This element here, 3, we looked at the subgroup generated by 3, and we, in fact, got all of the group, right? We recovered the entire thing. And so what the language that we use to describe this situation is that 3 is a generator. 3 is a generator of U7, right? Because if you look at all of its powers, it gives you the entire group. But 2 ain't, or is not, right? 2 is not. And there's this question that you can ask yourself. Given a unit group like U7 or U8 or U10 or U whatever you want, given a unit group like this, which elements are going to be generators and which are not? Turns out to be a very interesting question. Okay, turns out to be an interesting question without a simple answer. It's something you should really think about. Now, I want to point out that because, a little bit more language here, because U7 is generated by a single element. That is because U7 is actually equal to the subgroup generated by one of its elements, we call it cyclic. Okay, so a group of any kind is cyclic if it is in fact generated by a single element. Okay, so just to be absolutely clear, i.e., hold on, i.e., G is cyclic if G is actually equal to the subgroup generated by some little g, right, for some G in G. Okay, obviously not every group has this property. As a matter of fact, not every unit group has this property. Okay, U7 does have this property. U7 does have a generator, 3, okay, and it may have others as well, but not every unit group does have generators. And you can ask yourself which unit groups have generators, which unit groups are cyclic, right, generated by a single element, and which don't, and why? That is also an interesting question that you can do a lot of experimentation on, and I recommend you try to think about. The answer is not obvious, but not completely beyond the realm of your understanding either. So it's a good example to look at. Okay, so I think I wanted to do maybe just one more quick example, because I don't want to just talk about number theory, but just GLN. This thing here is the set of all n by n invertible matrices. Okay, this thing in fact forms a group under one operation, under matrix multiplication. Okay, so remember I said that the group operation can be all kinds of different things, and in this case, it is quite a strange operation, right? Matrix multiplication is not a simple operation. This in fact does form a group, and you can think about it and see why it's true. And I wanted to give you a special example of a subgroup of this group, okay? SLN, this is the set of n by n invertible matrices. Does anyone know? I wonder if we can call on someone. I assume Brian knows, but what's the extra property?
Susanth Satish Kumar says the determinant is equal to 1.
That's right, yeah. This is the special linear group. Instead of n by n invertible matrices with determinant 1. And this in fact forms a subgroup of GLN. So this thing is a subgroup of this thing. Pretty easy to see why. I mean, the key idea to see why is that if you take, two elements of this guy here and you look at their product and you compute the determinant, well, it's sort of a well-known fact that the determinant distributes over products. So this is determinant of A times determinant of B. So if A and B have determinant 1, then from this equation you can see that the determinant of their product will also have 1. So this thing is closed under matrix multiplication. So just another example of what a subgroup can look like. And there are billions of other examples. But let's move on. So what I've done is I've given you, for the last half hour, I've given you lots of definitions, okay, and examples. And that is all well and good, but we're here to do math, which means we need to actually write down some theorems and prove them. So that's what I'm going to do now. And I'm going to do what is a extremely important theorem in group theory called Lagrange's theorem. Okay, so let's talk about Lagrange's theorem. Realistically, there are probably like 12 different theorems named after Lagrange. You know, it's always sort of a mess. You know, certainly that's the case when you talk about Euler. Euler always has like 12 different things named after him. So this is the Lagrange theorem about subgroups and their orders. So just very quickly, I need one more definition before I can tell you what Lagrange's theorem says. So the order of a group, capital G, which we denote, so denoted G with absolute value bars, is just the number of elements in G. Okay, so the order of a group is just the number of elements that it has. You can have a group with an infinite number of elements. We've already seen some, like integers, right? By and large, infinite groups are a complicated subject, and we won't really talk about them here today. But yeah, if a group has a finite number of elements, and then its order is just the number of elements that it has. Okay, so here's the statement of Lagrange's theorem. So theorem, let H be a subgroup of capital G, okay? So it could be any kind of group, could be a group of matrices, could be whatever you want. Then the order of H, that's the number of elements in H, divides the order of G, that's the number of elements in G. Really quite a surprising fact, because groups are so general and abstract. You know, to be able to say anything like this about them is really kind of a wonder. Okay, well, let's prove it. So it's not a trivial proof. It's not too bad, but we do have to develop some machinery to prove this. We need to talk about cosets. Okay, so what I'm going to do is I'm going to define the so-called left coset of H by G. So I hope it's clear from context that I tend to use lowercase letters to represent elements. So little g here is an element, right? So define the left coset of H by G as follows. Okay, so I'm going to define this thing that I'm calling a coset. Little g, capital H. This is the notation that means the left coset of H by G, and it's a set, okay? It's a set of elements in G. Here's what it is precisely. It's the set of elements of the following form. GH such that H is in capital H, okay? So it's all the elements of this form. Little g, little h, where little h is in capital H. And I hope it's clear that little g is fixed, right? Like you fix a g early on, like you pinpoint it, you stick to it. It's the h's which are sort of variable. It's the h's which are ranging over all the elements of the subgroup H. Okay, so you can call those variable if you please, but little g is fixed in this quantity, right? Okay. So that's a left coset of H by G. So here's the picture that I want to sort of show you here. We have this group, G, which I'm going to represent as a blob. So here's G. Oops. Undo. Oh, no, I undid the whole thing. Okay, that's okay. It was just a blob. So we have this set G. This is our group. And what we have are these cosets, okay? What I want to emphasize is that these guys here, you know, each individual coset is a subset. So this thing here is a subset of G, but it is not in general a subgroup. I want to be clear about that. Cosets are subsets of G, but they are not in general subgroups. They're just smaller collections of elements of G sitting within G. And what I want to do is think about all the different cosets, because you could get different cosets, right? Like, for example, you could fix an element G1, and look at the left coset by G1. That would be some collection of elements. Or you could take some other element, say G2, and look at the left coset by G2, and that will be some other set of elements in G. And it turns out that the picture is something like this. So here are all the different elements in G. Okay, these little dots. I'm just representing the elements of G as little dots. Okay. And each one of these cosets is a subset, right? It's some sub-collection of these dots. So maybe G1H is this collection right here. It's these 4 dots, okay? And then maybe G2H, that other coset, is these guys, okay? And then maybe G3H, some other coset, is just these guys, and then maybe this guy here is G4H, okay? What we're going to be doing is looking at the different cosets. And what I need to do is prove a couple of things about these cosets. So one thing that I'm going to show is that the cosets don't overlap. What I really want to say is a little bit more precise than that. But basically what I want to say is that if you have 2 different cosets, they don't like run into each other. Like this one doesn't bleed into this one over here, okay? And then the other thing that I'm going to show is that every coset has the same number of elements. In particular, it has order of H elements, okay? So every one of these cosets has the same number of elements. In particular, it's however many elements are in the subgroup, and the distinct cosets don't overlap, okay? And these 2 facts are going to allow us to count the number of elements in the whole group in terms of the number of elements in the cosets, as we'll see. So this is kind of the game plan, okay? All right, so let me actually prove each of these things. So, 1, the non-overlap of cosets. So let's let G1H and G2H be 2 cosets, okay? I claim that there are 2 possibilities, okay? Either G1H is actually equal to G2H, like they're actually the same coset after all, or they don't overlap at all. They have nothing in common. Notationally, that means the first coset intersect with the second coset is the empty set, okay? So this is what I mean when I say the cosets don't overlap. If they're distinct, like if they're not actually the same coset, then they actually don't overlap at all. If you're familiar with the word, what I'm saying here is that the cosets form a partition of G. That's the fancy word for partition, okay? So how can I prove this little lemma? Well, here's what I'm going to do. I'm going to assume that this first thing is not true. I'm going to assume that, I'm going to assume that the second thing is not true. I'm going to assume that this statement's false. In other words, I'm going to assume that there's something in the overlap. So suppose there does indeed exist some G that is in both of these guys, okay? That's in both of these cosets. So in other words, I'm assuming the overlap is non-empty. And what we're going to see is that this assumption leads to this guy right here, okay? So if the overlap isn't non-empty, then the 2 cosets actually have to be the same. And that will prove this lemma, okay? So I'm going to show you that actually this leads to the conclusion that the 2 cosets are in fact identical. All right, so let's just unpack what this assumption means. G being in G1H implies what? It implies, well, let's remember what G1H actually is. GH is the collection of all things of this form, right? Where H is just any element in H. So G being in G1H implies that G has that form. In other words, G is actually equal to G1 times some element of H, which I'll call H1, right? For some H1 in H. That's what it implies. And then similarly, we're assuming that G is in both of these cosets. G being in the second coset, G2H, implies that G has to, be in the form designated by the second coset. Namely, it has to be of the form G2 times some element of H. Now, I'm going to call it H2 because this element of H doesn't have to be the same as this element of H. There's no reason for them to be the same, okay? So this is just for some H2 in H. Okay. Now I hope that looking at these two guys right here, you're like, oh, I know what to do. I know what to do. Actually, does anyone know what to do? What should I do? Any thoughts looking at these two equations here? Brian, if you want to call on it, because I can't see anybody.
Feel free to unmute yourself if you want to respond. Anyone?
I feel like, really? Looking at these two equations here, you're like, I have no idea what to do with that. Nothing jumps out at you. I give you these two equations. Okay. All right, guys. Well, look, what you...
Okay.
Sorry?
Transitive and multiply them.
Yeah, transitive property, right? I mean, if G is equal to this and G is also equal to this, I can set these two bad boys equal to each other, right? I can say, oh, that means the G1 H1 has to be equal to G2 H2. G1 H1 is beginning to sound like the swine flu virus or something. Okay, so G1 H1 equals G2 H2. Now, here's what I'm going to do with that. I'm going to solve this thing for G1, all right? Now, these are group elements, like not literally numbers. So if your intuition is to divide both sides by H1, that's basically right. But we have to be careful. What we have is we have inverses. I can multiply both sides by the inverse of H1, whatever that is. I'm certainly allowed to do that, okay? Because I know that every element has an inverse. This is a group, right? So I'm allowed to do that. And then what do I know about when you smash together an element with its inverse? You get the, by definition, you get the identity, right? So this is G1 times E, the identity. And then I'm not making any further changes on the right-hand side. H1 inverse. And then, of course, G1 times the identity, well, the defining property of the identity is that it doesn't do anything, right? The identity doesn't do anything. So left-hand side is, in fact, just G1 equals G2, H2, H1 inverse, okay? Now, why is that useful? Well, here's what I'm going to do. I'm going to pick an arbitrary element of that first coset, G1 capital H, okay? What does such an element look like? What does an arbitrary element of that set look like? It looks like G1 times some H, right? I'll use H with no subscript. I haven't used that yet, okay? That's what an arbitrary or random element of this coset looks like. Now, this thing is equal to, using this equation here, I can replace the G1 with that expression and write G2, H2, H1 inverse, and then H. Now, here is something very interesting. This string of three elements, H2, H1 inverse, H. But you remember what they are. They're all, H is an element of capital H, right? It's an element of the subgroup. H2 is also an element of the subgroup. Now, H1 is an element of the subgroup, and we know from the definition of a subgroup, the inverse of an element of a subgroup is also in the subgroup, right? So all three of these guys are elements of the subgroup capital H, which means their product is all an element of H. So this whole thing right here is really just one big element of H. And the thing to understand is that it's telling you that this whole expression here, consider its form. It is of the form G2 times some element of H, right? That is the overall structure of this expression, G2 times some element of H, which means it is an element of G2 capital H, because G2 capital H is the collection of all objects of this form, G2 times an element of H. That's what this thing is. This thing has that form, ipso facto, it's got to be in that set, okay? Now, what I've done is I've shown that an arbitrary, or if you like, random element of the coset G1H happens to be inside of G2H. Okay, if a random element of this guy is always inside of this guy, that means that this set is in fact contained inside of this set. So the first coset is actually contained in the second coset. Okay? And the thing that I want you to notice now is that, you know, I could have made this whole argument that I just made, right? Starting from, boy, I guess it was here, right? I'm trying to prove that if there's any element inside the overlap of the two cosets, then the two cosets are the same. That's what I'm trying to prove. And, you know, what I did was I proved that G1H is actually contained in G2H. But you can reverse the entire argument, right? You can do a mirror image like proof just like it, but instead of working with G1, you work with G2. So an identical argument to the one that I just did shows that G2H is contained in G1H, okay? So, you know, if you have two sets and each one is contained in the other, like this guy is contained in this guy, but also this guy is contained in the other one, that is what we mean when we say the two sets are equal, okay? That means that G1 is actually equal to G2H, okay? So that's what we wanted. What we showed is that if there is anything in the overlap of the two cosets, then those two cosets have to be equal. That's what we showed, okay? So that proves my lemma here. Either the two cosets don't overlap at all, or if they do overlap at all, if they have anything in common, they actually turn out to be the same. Okay, that's the first thing. Now, the second lemma that I needed to prove Lagrange's theorem is that every coset has the same number of elements. It has, in fact, order of H elements. However many elements are in H, that's the number of elements total, okay? And that's actually a lot easier to prove. And so let's just prove that. So basically what you need to do is the following. Here's a picture, okay? Consider H, the subgroup. And maybe H has some elements. Here's an element, here's an element, here's an element, okay? And then here is a coset, GH, okay? And it is also a collection of elements. I claim that this guy here, the coset, has the same number of elements as the original subgroup H. And the way to think of it is the following. There is a function you can define from here to here, or if you like, a map that goes from here to here, which all you do is you multiply by G. So let me be clear about what that means. Let's give these dots some names. Let's say this is G1, or sorry, not G1. I want to call them H's because they're elements of H. Let's call this H1, H2, H3, and H4. And then smash little g against each of these elements here, all right? You'll get GH1, some element here, GH2, some element here, GH3, some element here, and GH4, some element here, okay? Now, in the picture that I've drawn, there are 4 elements to begin with, and then there are 4 elements after we're done. And this picture seems to suggest that the number of elements is the same in both sets. but the picture could be misleading. There could be something going wrong. And maybe someone can tell me what could go wrong about this argument. Why might it be the case that actually this set here, the coset, doesn't have the same number of elements as the original set here, H? What might go wrong? Any ideas?
Ambarish Shyam Sundar says the map isn't one-to-one.
Right. It might not be one-to-one. In other words, for example, GH1 and GH2 could actually be the same element, right? That could happen. In which case, this guy would only have, say, 3 elements, whereas the original one had 4. Okay, so that's the thing. That's the only thing that could go wrong here, is that the map might not be one-to-one. But let's suppose that that happens and see what that implies. Okay, let's suppose that 2 of these guys over here actually are the same. All right, let's suppose that, say, GH1 is equal to GH2. Okay. What I can do is I can multiply both sides by the inverse of G, right, on the left. And I get this. And just like before, these 2 guys, GG inverse is the identity element, right? So this is really just EH1, and EH1 is just H1, right? They cancel, essentially, right? And same deal here. So what this is telling you is that actually the map is injective, right? Or it is one-to-one, right? If 2 elements over here are the same, that actually means the guys they came from were the same to begin with. So there's no collapsing of elements, right? It just doesn't happen that 2 things get sent to the same thing, because if they get sent to the same thing, that means that the 2 things were the same to begin with, okay? So this doesn't happen. So let's now just think about what we've shown. We have shown that in this picture of G, we've got all these different cosets. And what do we know now? We know that the cosets they don't overlap at all, right? Or rather, distinct cosets don't overlap. And we've shown that they have the same number of elements. And I said that we can use this to count the number of elements in G. There actually is one little wrinkle that maybe we should talk about. I don't think I'll write anything. You have to show that every element in G is actually in one of these cosets. Like the cosets actually cover G, but that's actually pretty easy to show because an element G is always in GH. And why is that? Because remember I said that the identity element is always in H? Well, that implies that the element GE is in GH, but of course GE is just G itself. So every element G is in the coset GH. So that proves that every element in G is in fact in one of these cosets. So we can use all these ideas to count the number of elements in G. So here's what we can say. The order of G, that is the number of elements in G, is going to be equal to, well, what? The number of elements in the first coset, G1H, plus the number of elements in the second coset, G2H, plus all the way up to, I don't know how many distinct cosets there are. Let's just say it's N, GNH, okay? And these guys are the distinct cosets, okay? These guys are the distinct cosets. And however many there are, I don't really know, but what I've shown is that every one of these cosets has the same number of elements as H itself. So I can replace every instance of this, number of elements in the coset with just number of elements in H, plus number of elements in H, plus all the way up to number of elements in H. And that, of course, is going to be, N times number of elements in H. So we can see that the order of G is equal to N times the number of elements of H for some integer N. And that proves that the order of H divides the order of G. Okay, so that is Lagrange's theorem. Really wonderful theorem. a cute little proof. And I'll just spend a few minutes showing you an application, and then I'll take questions. So let's go back to so here's a proposition, and I won't prove it. I'll leave it to you to sort of think about. We can talk not just about the order of a group, or not just the order of a subgroup. We can also talk about the order of an element within a group. So if if X is an element, let me stick with G. If G is an element of capital G, then the order of G is the smallest number, or the smallest power, I should say, that gives identity. Okay. So going back to the unit groups, I can show you what that means with the example that we did up here. So if I go back to these unit groups, we looked at the subgroup generated by 3, the subgroup generated by 2. What is the order of 2 in this example? It was 3, right? Because 2 to the first is 2, 2 squared is 4, and then it's 2 to the third, which gives you the identity element. So the order of this guy was 3. And what's the order of 3 in this group? It was, let's see, 1, 2, 3, 4, 5, 6. The order of this guy was 6, okay? So that's the order of an element. It's the smallest number, it's the smallest power which gives you identity when you raise that element to a power. And the proposition here is that the order of G also divides the order of the group. And I'll let you think about why that is. Okay, you can use Lagrange's theorem. So the order of an element also divides the order of the group. And let's return now to the unit groups, okay? I'm gonna look at another unit group, all right? But I'm not gonna look at U7. I'm not gonna look at U5. I'm gonna look at U250, okay? This is a really big group. It's all the numbers that are relatively prime to 250, right? There's a lot of numbers in there. There's a fact from number theory, basically the Chinese remainder theorem, more or less, tells you that because 250 is equal to 2 times 5 to the third, that's the prime factorization. You can show pretty easily using the Chinese remainder theorem that this implies that the number of elements in the unit group is 2 minus 1 times 5 to the third minus 5 squared. That's just kind of a formula from number theory, which gives you brain not functioning 100. Is that right? No. Yeah, that's right. That's 100. 125 minus 100. So the number of elements in here is 250, all right? Now here's the question I'm gonna ask you, and this is sort of the last thing that I'll say. Is 2 a generator of U250? Okay, and remember what that means. That means, if I take repeated powers of 2, like 2 to the first, 2 squared, 2 to the third, and so on, modulo 250. If I look at all those powers, do I get all the elements in this group? Do I get all of them? Okay. Now, there's 100 elements in this group, which means theoretically, you would have to check 100 different powers of 2. You'd have to check 2 to the first, 2 to the second, 2 to the third, and so on, all the way up to 100. That's a lot of things to check, right? But then remember what the proposition I mentioned just a moment ago said. The order of an element divides the order of the group, okay? Which means that since this group has 100 elements, the order of 2 must divide 100, okay? So 2, its order, it could be 2, or it could be 5 or 10 or 50, but it couldn't be 77, right? Like, it cannot be that 2 to the 77 is equal to 1. because that would be saying, you know, the order of 2 is 77, but 77 doesn't divide 100. So that can't happen. So you don't.
I think 2 is not. Kevin Doctor says that 2 is not a unit. I think he chose.
Oh yeah. No, you're absolutely right. That's a great point. This is what I get for like writing without thinking. But everything that I've said could just as well be said for 3, right? So indeed, 2 is not a unit because it's not relatively prime to 250. So I should be saying 3. It's an excellent point. But anyway, so all of what I just said applies just as well to 3, right? So is 3 a generator of U250, right? So we have to look at 3 to the 1, 3 squared, 3 to the third, and so on. But because of this proposition, we know that the order of 3, right, divides 100, right? Which means that we actually only have to check the divisors of 100, right? So like, you just have to check and be like, oh, is 3 squared equal to 1? I mean, it's obviously not. Is 3 to the, what's the next smallest divisor? I guess 4. Is 3 to the 4, right? And you could check that. And so that reduces the number of things that you have to check by quite a lot. However, I claim that you can actually do even better than that. You can actually do even better than checking all the divisors of 100. And I'll let you think about sort of the minimal list of powers that you have to check to verify that 3 is a generator of this group. I have no idea if it is a generator or not. Indeed, this group may have no generators. Okay, so I think that's a good place to stop and take questions or comments or anything like that.
I think you need to click on the chat icon on your screen. It's on the right-hand side.
Ah, here it is. And you have to forgive me. I've used Google Meets approximately 2 times, including this time. Yeah, very good point about the 2 not being in U250. It's not relatively prime, right? So 20, yeah, so 20 and 50. What leads you to say 20 and 50 only, August? Yeah. So Dennis is sort of talking about, you know, what you sort of want to think about is like, you know, the divisors form kind of a tree, right? So I mean, you've got like 100, and then you've got, you know, which of course is 2 squared times 5 squared, right? Yep. So you can sort of make like a tree like this, sort of omitting just one factor. And if you think about it, every other divisor have to sort of divide one of these. That sort of reduces the list that you have to check. But yeah, so that's something that comes directly from Lagrange's theorem. I'm sure that there are other ways of thinking about it without Lagrange's theorem, so does the order of an element always have to exist? Yes, in a finite group. In a finite group, an element has to have a finite order. Now, in an infinite group, an element may have an infinite order. For example, in the integers under addition, 1 itself, you can add 1 to itself as many times as you like. You're never going to get to the identity 0. So that, in fact, most elements, you know, have an infinite order. But for finite groups, elements have a finite order every time, basically because of like exhaustion, right? I mean, if you repeatedly apply the element to itself over and over again, you eventually have to loop back around, and you can sort of show that you exhaust everything. I saw Brian Go had a question about abstract algebra.
I think you need to scroll down.
Oh, so I do, my bad. What is the difference between linear and abstract algebra? Abstract algebra is broader Linear algebra specifically refers to the study of vector spaces and the maps between them, namely linear maps, which are represented by matrices. I suppose advanced linear algebra gets into things like tensor products and modules. Abstract algebra is a broader category. It includes linear algebra, but also group theory, ring theory, field theory, and other things as well. Is abstract algebra focused only on group theory? No, as I said, yeah, there's lots of other things in addition, not just groups. But broadly speaking, abstract algebra is the study of structures with bones, I would say, as opposed to something like analysis, where the structures involved are sort of continuous, and you can sort of zoom in as much as you want. It's sort of smooth and everything. Structures that you study in abstract algebra have a skeleton. They have a discrete structure, generally speaking. How do abstract algebra be needed in quantum mechanics? In quantum mechanics, well, you need lots of linear algebra for quantum mechanics. Quantum mechanics also uses a lot of something called representation theory. And that falls under the umbrella of abstract algebra. Representation theory is a way of taking information about groups and translating it into information about vector spaces. Vector spaces are generally better behaved than groups. So, and then finally, is there any application of abstract algebra in physics? Oh yeah, absolutely, 100%. Like quantum mechanics is definitely one of them. And you know, I mean, linear algebra is used all the time. Especially a lot of the classical like Lie groups, like the special orthogonal group, and these like rotation groups show up all the time. And I know in like particle physics, the setting that they use for studying like the standard model, the mathematics of the standard model is something called principal bundles. And there's, that's really kind of a combination of geometry and algebra, but in a principal bundle, there's like a group which is acting on something. So groups are like very closely embedded in that theory.
Oh, it'll be uploaded to YouTube, and a link will be sent out for everyone to who missed the lecture or wants to review the lecture to see.
Yeah. Any other questions, guys? Cool.
Okay. All right. Thank you so much for coming and presenting for us.
Yeah, my pleasure.
I'll give Mr. Knott a round of applause.
Thank you, guys. Nice.
All right. All right.